Buenos dias, muchachas y muchachos. Welcome again to another edition of Honors Physics. It's Mr. Finn coming to you from neighboring Northville, trying to get you some stuff on Coulomb's law today, as well as reviewing a little bit of polarization and some of those ways of charging that we were looking at yesterday. Before we get into that, though, a couple of quick announcements. Number one, the Google form. Every week, at the end of every week, we're going to do a Google form for the remainder of the school year. So, since our end of our week is tomorrow, Thursday, I will be having a 5-question Google form for you to fill out regarding the content of this week. And we'll do that every week as a way of supplanting our weekly quizzes or any kind of homework that we might have turned in. So I do have some extra activities I'm trying to get to you, but I've been locked out of the school, so everything I have I just got to do with what I've got until I get back into school and get some of my materials. All right, second announcement. So I'm sorry, Google form between 3 p.m. and 6 p.m. tomorrow, Thursday. Second announcement. If you have a missing assignment from the first 8 weeks, that means the 8 weeks that we were together in class. A missing assignment is not a poorly done assignment. A missing assignment means you did not hand it in. I can take a unit set of problems and evaluate that for the homeworks that you missed. So if you missed a collection where 2 homework problems were collected, you can email me a copy of the entire unit of work. For example, the sound section, if I collected anything from the sound section or the wave section, you could give me the problem set for that entire unit as a makeup, and I'll evaluate some of the points there. Okay, so this is not if you're missing points that you already handed in an assignment, you just lost a couple points. So if you got an 8 out of 10 or a 9 out of 10 on a homework collection, you're just going to have to stay with that. But if you got a 0, definitely want to make sure I can get you some points if you can give me the unit work for that. Okay? Does that sound good, guys? All right. So yesterday, we talked about charging by conduction. Charging by conduction. So what I'm going to do today is I'm going to show a quick demonstration involving polarization. And maybe we can work into a new type of relationship regarding attraction. We had the wall and the balloon yesterday, or 2 days ago. But today, I want to do another quick demonstration. So let's do that now. Okay, guys, for this demonstration, I just got a regular empty soda can here. You can see there's nothing special about it. It's just sitting on the table. And I'm going to use my fur and my rubber rod again. And what I'm going to do is I'm going to charge the rubber rod by using a little friction. We learned that a couple days ago. And I'm going to place the rubber rod close to the can. Close. There we go. Can's following me. Close. And so what happens is that we can probably measure the acceleration of this can. Okay, guys, how are you doing today? Well, we had a can attracted to a charged rod. Now you can see the can was moving pretty good. That could be an acceleration that we could measure. If we could then divide by the mass of the can, or multiply by the mass of the can, we would get the force of attraction that the rod had with the can. Now remember, it's the same force that the rod attracts the can as the can attracts the rod. So we only need one of those pieces to work out the actual force. But let's take an example of Coulomb's law, which is a relationship of electric force, K, Q1, Q2 over D squared. That looks a lot like the gravitational law, where F equals big G times M1, M2 over D squared, where D would be the radius of the Earth or the distance between the two objects that are gravitationally attracted. It's very similar. And K is an electric constant of the universe, and it's 9 billion Newton meters squared per Coulomb squared, or 9 times 10 to the ninth. That's always going to be the case. But the charges will change. What are those Q's? Those are individual charges, Q1 and Q2, separated by a distance. And that distance would be the distance between the charges. So what I have today is a simple version of Coulomb's law worked for two electrons, so a negative here and a negative here, but they're separated by about 1 millimeter, which is 0.001 meters. 1 millimeter. 1, 2, 3. Just move the 3 decimal places and you'll have 1 millimeter in terms of meters. So what happens here? Well, sticking everything into Coulomb's law, we'd have 9 times 10 to the ninth Newton meter squared per kilogram squared, and I've canceled the units to show you how it works. 2.56 times 10 to the negative 38 is the charge of an electron squared, because one electron's charge is 1.6 times 10 to the negative 19th coulombs. If you had that over here, and another, actually this should be negative. These charges should be negative, but because they're squared, it's going to cancel out anyway. But negative 1.6 times 10 to the negative 19th coulombs for one electron, and another negative 1.6 times 10 to the negative 19th coulombs for an additional electron, those values are multiplied together. So if I have the same charge, I can just square Q1 and Q2 becomes Q squared. Either way, 2.56 times 10 to the negative 38. Now I'm doing it in steps, and there's a reason for that. Because in your calculator, if you don't use parentheses around those big numbers, your calculator will work in the order that you entered the information, and you'll come up with a very different answer. So I need you to walk through this with on your calculator to make sure that you've got the steps right. Remember, enclose big numbers in parentheses. Down below, I've just expanded 0.001 meters by a square value. So if I expand that, it becomes 0.000001 meters squared. Okay, no problem. So I get rid of the parentheses, and my meter squared cancels with meter squared up here. My Coulomb squared cancels with Coulomb squared there, and I'm left simply with newtons, which is good because I want to be in force. I've got to be measuring in newtons. Now, if I measure 9 times 10 to the ninth by 2.56 times 10 to the negative 38th, what I actually get is 23.04 times 10 to the negative 29th. Now I know we're supposed to express this in scientific notation, where the number, the beginning, must be between 1 and 9. But if I don't have a calculator, I can do this kind of in my head, because I can multiply 2.5 times 9. 9 times 2.5 is 22.5, right? So it should be pretty close. 2.25, not 2.304. But 9 times 2.5 would give you 22.5. But 10 to the negative 38 multiplied by 10 to the ninth, you're supposed to add the coefficients when you multiply the base of 10. So 10 to the negative 38, their negative 38 plus 9 is a negative 29. So I'm pretty close to that. Now obviously in your calculators, that would give you that in real scientific notation. And that's okay. Just make sure you can do it a little bit in your head to get an idea of what the answer should be around. Well, this number is 1 times 10 to the negative 6th. So 2.3 times 10, or 23 times 10 to the negative 29th divided by 1 times 10 to the negative 6th. My answer should be on the order of 10 to the 23rd power. And don't forget you have an extra place value of 2 there. So that makes my answer on 10 to the negative 22nd. But 2.3 times divided by 1 is simply going to be 2.3. Now, if you look this through in your calculator, you should get around 2.3 times 10 to the negative 22nd newtons. And that's exactly how much force would be between two electrons that are 1 millimeter apart. Now, of course, two electrons might also be forced by other charges around, but you get the idea. We can use Coulomb's law as long as we have the charges involved and the distance between them. Now for our can, we could have actually measured the acceleration of the can and the mass of the can. That's Newton's second law. If we did that, and we assumed that the charge on the can was the only charge, well, we know the can is polarizing. So we may have to do a little bit of digging there. But you get the idea of how to use Coulomb's law. K Q1 Q2 over D squared. In this case, we have the same charges, so we could use Q squared instead of Q1 and Q2. Okay, guys, I hope that's okay with Coulomb's law. You do have some practice problems for homework, so I'd like you to try those and get back to me and see how you do. Yesterday, we also talked about the three ways of charging, or two ways. We had friction, that's charged by rubbing, and the two surfaces are not the same, so one surface has a propensity to give up its electrons to the other. And we also had this charge by conduction. So if I charged up my rubber rod, and I touched the ball on my electroscope, well, you can see that now the charge is present in the electroscope because the needle remains deflected. After it comes to rest, it'll be in a deflected spot, showing the presence of charge on the scope. So what if I put more charge on an object, and I brought it near the ball again? You can see as the balloon comes in, my needle deflects even more. So when I bring a negatively charged object close to a negatively charged scope, the needle will further deflect because electrons that are still in the ball, even though they're in excess of the electrons that are in excess of the protons in the scope, more electrons coming into the picture will force some of these electrons to run down into the scope that aren't currently there. And they will run to the bar, deflecting. So, bringing a negatively charged object close to a negatively charged scope means the bar deflects even more. More electrons run down to the bar, attempting to get away from other electrons. You guys got that? We also covered the aspect of grounding. If I simply touch the ball, the needle eventually goes back. Maybe you can think about this, and we'll address the rest tomorrow. What I'm going to do is I'm going to charge this balloon. You can see the scope has no charge on it at the time. So I'm going to charge the balloon a little. But this time I'm going to touch the scope. I'm going to bring the balloon in, take away my finger. Now you can see that the balloon didn't even get nearly as close as it was the last time. But I do have a presence of charge showing on the scope. So remember, we just learned that a negatively charged object brought close to a negatively charged scope would deflect the needle even further. So what happens if I bring a negatively charged balloon in now? You can see the scope goes the other way. The needle on the electroscope actually becomes closer to neutral, not further away, as in the previous example. And the only change was the fact that I had my finger on the scope. I'll do it one more time. Bringing my electric charge in. You can see that the scope deflects closer to neutral. I'd like to have you guys think about that, and we'll address that one again tomorrow's video called induction. Okay? But great job today, guys. And let's take a few moments to do some Coulomb's law questions and problems to make sure that we're good there. It's the fundamental force for electric force. So we're going to need to understand that fairly well. As a reminder, we do have a Google form tomorrow. I'm going to try and make it available about 3 p.m. But it's just 5 questions. But if you can get that done between 3 and 6 tomorrow, and we'll go ahead and keep track of your grades on Google Classroom. Keep up with the videos, guys, and as always, if you have questions, please send them along through the email chain, and I'll make sure to answer those in the next video. Have a great day, guys, and we'll see you tomorrow.